Hi all, in this lesson we calculate the confidence interval for the mean using a t-interval instead of a z-interval. The biggest difference here is that we use the t when sigma is unknown and we use z when sigma is known. So let's figure out how we know when sigma is known. Here are some clues, and if I were you I would print this slide out and use it when you do your homeworks and tests. Sometimes they will say sigma equals, which is the most obvious that sigma is known, or the population standard deviation is, or the standard deviation is known to be, or assumed to be. You have to really read the problem and assess it if what you are given is the population standard deviation. So how do you know if sigma is unknown? You still are given a standard deviation, but the standard deviation is the sample standard deviation. So they might say S equals, which is the sample standard deviation, and therefore we don't know sigma. Or they may say the sample standard deviation is, and the third way may be the most common, where they say the mean of the sample is some value with a standard deviation of some other value, which is another way of saying the mean and the standard deviation both come from the sample. And sometimes the standard deviation may not be given, but they will give you the data and expect you to calculate it, which is the sample standard deviation. And again, the formula in the previous slide we use only if sigma is known. But when sigma is unknown, then the formula is pretty much the same besides the distribution. We use the t distribution instead of z, and then the other difference is that we use s instead of sigma. And make sure you know the difference between sigma and s, because that is what is going to tell you which formula to use. So I'm not going to tell you on the homeworks or tests which formula to use. You will have to figure it out. So make sure you understand the difference. So let's talk about the t-distribution. It starts with because sigma is unknown, we are estimating sigma with s. So now we have an estimate for sigma being used to help generate an estimate for x bar. So there is an extra variability, which we need a distribution that is almost the same as z, but a little bit more spread out, which is what the t-distribution is. Another requirement is that we also need to know that the sample size must be large and or the data follows a normal distribution, so one or the other can be true. In order to tell this, you can graph the data or it states it in the problem. So the same requirements are true for the z-interval, but I don't emphasize it as much since we normally use the t-interval. So always check to make sure that these requirements are met. In one of the homework questions I just want to mention, it asks what does it mean for the t-interval to be robust against violations of normality. All that means is even if you don't have a normal distribution, you can still use the t-interval if the sample size is large. And in most cases, the t-interval is used instead of the z. It's just the z-interval is not really used much in reality. So a little bit more about the t-distribution. They are shaped just like the standard normal, but with a larger spread. The amount of spread is determined by the degrees of freedom, or df, which is just equal to n minus 1, which is sample size minus 1. And your book goes into a definition and it explains it a little bit, but all you need to know is that degrees of freedom equals sample size minus 1. So the t-distribution is still bell-shaped, and it's more spread out than the z-distribution, but as the degrees of freedom increases, the spread decreases and becomes similar to the z-curve. So when we have a very large degrees of freedom, that would mean we also have a really big sample. The t and the z are basically the same. And you can see that by looking at the table. Let's pull up the table real fast. Here are the degrees of freedom on this, and here is the area and the two tails. and the one tail, but we're going to be using the area and the two tails. We want this area, and this area is 1 minus our confidence level. So for a 99 degrees confidence interval, we'll want this column right here. And that's because it's 1 minus 0.99, and that gives us 0.01. And then for a 95% confidence interval, we'll look at this middle column right here. And then for a 90% confidence interval, we'll look right here at 0.10 column. So we'll look for degrees of freedom, which is n minus 1, and then we look for the area under the two tails to get the t-stat in the middle. So let's go back and do a couple examples. So the first example, let's find the value for t alpha over 2 for a 90 degrees confidence interval and n equals 25. So since n equals 25, our degrees of freedom is 25 minus 1, which is 24. So, and we want a 90% confidence interval. So we're going to look at this column right here, and then we're going to look for the degrees of freedom 24. So scrolling down, so 24, and we get 1.711. So going back to the slides, and that's our t value. And then here, let's do another example. We want to find a t-value for a 99% confidence interval and a sample size of 12. So our degrees of freedom will be 11, and we want to look at this column because it's a 99%. So 11 and 99%. We get 3.106. And that's the answer. Okay, so here's the formula for the t interval. The two differences again are that we use t instead of z, and since we don't know sigma, we put in s for sigma. So here's an example. We have 10 tulip bulbs planted, and their heights are right here, and we want a 90 degrees confidence interval. So you can use StatCrunch for this to calculate the mean and the sample standard deviation. So we have a sample mean of 15.230 and a sample standard deviation of 2.484, and the sample size is 10. So the degrees of freedom is 9, and they wanted a 90%. So we have our degrees of freedom is 9, and they wanted a 90%, so we look at this column. So our t is 1.883. So now going back, we use that formula. So our formula, we use our sample mean plus or minus the t-value we just got times our sample standard deviation divided by our square root of our sample size, which is 10. So this side is our margin of error, and we get 1.440 if we put it in the calculator. So then 15.230 minus 1.440 gives us this side, the lower limit. And then if we do 15.230 plus 1.440, we get 16.670 is the upper limit. So that means we're 90% confident that the mean height of all 4-month-old tulips is between 13.790 inches and 16.670 inches. And again, I would like you to know how to do them both in StatCrunch and by hand so you really understand these problems. So I provided some example videos that please watch them. They'll help you guys a lot. So that's it.